Thanks for staying until the last talk. It's a great workshop so far. Yeah. So, all right. So I'm going to be talking about some joint work with some people at Google and. Okay. So. Okay. Be careful not to press this. Okay. This is some people at Google and some collaborators of ours. So the general question I want to talk about is how do you construct expander graphs locally? Okay, so there are lots of known constructions for expanders, but many of them rely on strong global structure. Okay, so remember that expansion itself is a global property. Okay, so what do we mean by this question? So let me motivate this by giving a concrete example. Okay, so one example is peer-to-peer networks. So you have a collection of nodes, and they all want to talk to each other. Think of them as a bunch of nodes that are all interested in, some particular file in a file sharing system. Okay, so every node is it can talk to anyone it wants, but at every time step it only communicates with a few neighbors. Okay, so there's a set of neighbors at every time step, and it only communicates with them. And this is what we mean by local here. And the goal is you want to end up with a very well-connected network, in this case an expander. And what you're allowed to do is a node can decide to change its edges and connect to somebody else. Okay? But it has no idea of the full network. It only knows of its neighbors at its current step. Okay? So this is a fairly realistic model. And one question you can ask here is, starting with some connected graph, is there some simple protocol you can run so that you end up with an expander? Okay, so this in the file sharing example, for instance, this allows really good connectivity afterwards. Okay, and we would like some nice things about this protocol. For instance, every node should use a small amount of memory, and all the message sizes should be small, and so on. Okay, and it's good also if it's asynchronous. So it turns out this specific problem has been studied. There's quite a bit of work on this. And the best known result is actually close to the best possible. And it's a generalization of what are called skip lists. Okay, so it's a graph generalization, which they call skip graphs. And what they give is a protocol that runs in something like log squared n rounds. And each round you do a linear amount of communication, and it obtains some kind of a hierarchical graph. But there are a bunch of limitations for these kind of approaches. One is that firstly, it's a fairly involved algorithm, and it's a very coordinated algorithm. It's a very synchronized algorithm. And the message sizes are also, they tend to be quite big. Okay, so the total amount of work is bounded, but individual message sizes could be quite big. Also, the node memories could be quite large. Okay? So the question I'll try to address in this talk is are there very simple protocols that allow you to end up with expanders? Okay? And to get inspiration for this, we look at a different line of work. Okay? So this is an unrelated question, which is you want to construct a random graph with a given degree sequence. Okay? So I give you a set of degrees, and the goal is to construct a random graph with this degree sequence. Okay? So this again is a very well-studied question in Markov chain theory. Okay? And most of the known algorithms for this work as follows. You start with some graph that has this degree sequence, and you make some random changes to the edges while somehow preserving the degrees. Okay? And you usually have to show that if you do a small number of such changes, you end up with a random graph. Okay, so you mix in the space of all graphs. So one very simple procedure, so the key to this, as you know, is how you make these changes to the edges, right? So how you change the connectivity. And one simple procedure was suggested is what's called the edge switch. So this was studied like more than 3 decades ago. And the idea here is you take 2 random edges in the graph, okay? And so you remove UV and RS, and you add these 2 edges. Okay? So this preserves all the degrees. Okay? And you move from one graph to the other. Okay, so and what Cooper and others showed is that this converges in polynomial time to what's called the configuration model. Okay. All right, so this is a very simple way of moving from one graph to the other. Okay, but there are a bunch of issues with this, and the first is that it's very non-local, right? Because if you have some edge UV and you want to figure out some other edge to swap with, you have to pick a uniformly random edge from the rest of the graph. Okay, we just saw that picking vertices itself is difficult, so picking edges is also tricky. And also this process could end up disconnecting the graph. Okay? And in some applications you might want to actually sample, you want to actually get a random connected graph. Okay? So for these kind of applications this process doesn't work. Okay? I mean preferably you want to be connected at all times, although you actually care about just the end, because you want to generate some random thing. All right. So a related thing that was proposed in 2005 was what's called the edge flip. Okay. So this is a way of it's a way of transforming graphs that looks very similar to the switch, but it keeps the graph connected and works as follows. Okay. So you look at a length 3 path in the graph. So let this be the length 3 path, and now you swap the two outside edges. Okay, so this is the two end edges. So you remove RU and VS and add these two edges. Okay. So it's easy to see that this also preserves degrees and preserves connectivity, more importantly. Okay. And this also has a natural interpretation because it's local, because it's like saying you have a network and two people who have an edge wake up and they decide to swap a random friend. So that's roughly what's going on here. So it's a very easy to distribute kind of an algorithm. So people can run this locally. Okay. And this indeed, experimentally, it has some really good properties. So it turns out that you actually look like you're converging. And in fact, the first polynomial time convergence bound, so it turns out this also converges to the configuration model. The first polynomial time bounds were shown by Feder and others, and they show a bound of, it's polynomial, but it's a fairly big polynomial. Okay. And this was then improved by Cooper and Dyer, and they improved the bound to something like n to the 14. Okay. So this is still quite bad, right? Because experimentally, it looks like something like ND operations seem to suffice. And how do you measure if you have mixed? Experimentally, people just see if the graph you obtain has a small diameter and things like that. No, D is I should have mentioned this. So I'm looking at D-regular graphs for now. Yeah. All right. But there's a reason these bounds are quite bad, and that is that they all go through Markov chain comparison type arguments. Okay, because you actually show that you mix in the space of all graphs that have degree D. Okay. All right, but experimentally it looks like you obtain like nice small diameter random looking graphs in roughly O of ND steps. Okay, so now the question is, can you explain this? And this is what we mainly show. So what we show is we can't quite show ND, but what we can prove is that if you have any connected D-regular graph, and D is not too small, it's at least log n, okay, then we can show that if you do something like n squared flips, okay, so flip again, remember, is this length 3 path and then you change the corner edges. So we show that you get an expander with extremely high probability. So this is the main result, and note that the exponent is now significantly better. Okay. All right. So before I continue, so I'll show you what goes into the proof of this, and there are some nice connections we'll make along the way. Okay. So before we go on, just to bring us all into the same page, let's just define expansion. So suppose you have a Okay, so suppose you have a deregular graph, and the conductance of some set of vertices. Suppose you look at some particular cut. Conductance is basically the number of edges going outside divided by the total number of edges incident on one of the sides. Okay. And you call G an expander if for all sets that are at most half the size, you have that this conductance is at least alpha. Okay. So this is how you define an alpha expander. And there's a very related notion, which is more algebraic notion. It's what's called algebraic expansion. And it basically says that if you look at the Laplacian of the graph, the second smallest eigenvalue has to be at least a constant times the degree. Okay. So, and the Laplacian, for those who are not familiar, is basically the diagonal matrix of degrees minus the adjacency matrix. Okay. All right. So this is just the definition of an expander, which most of you will be familiar with. Okay. And so this is the sense in which we show our results. So we show that you actually, after n squared steps, you end up with a spectral expander. Okay. And for constant expansion, both spectral and the previous notion are both equivalent. And as I said before, we conjecture that only something like nd steps suffice. Okay. So the best we can prove is n squared d squared. All right. So before explaining this result, I want to just mention why you expect this kind of flip operations to end up with a well-connected graph. Okay. So to see this, let's look at a graph that has a sparse cut in it. Okay. And what do we expect to happen when we do a bunch of flip operations? Okay. So suppose you take the extreme case, you have two deregular pieces, and you have exactly one edge going across. Okay. So in this case, most of the flip operations will actually be inside these, in which case this cut, nothing happens to this cut. Okay. But when you do have the middle edge of the flip being this UV, okay, then what you'll end up doing is you'll pick some edge out of U, some edge out of V. Okay. So in this case, these two. And you'll replace these two edges by edges that go across. Okay. So you end up increasing the cut size by 2. Okay. And so this kind of phenomena, you expect it to happen as long as vertices on the boundary of a cut have most of their edges actually going inside the cut. Okay. So if the cut is sparse, you expect it to improve. Okay. So this is the intuition for why you expect this kind of a procedure to work. Okay. But it turns out making this formal as is actually pretty tricky. And in fact, you can actually come up with pretty sparse cuts that don't improve. Okay. Because in some sense, it's only the vertices on the boundaries that matter. Okay. So you could have two huge sets, vertex sets, but edges that go between these sets are all focused on a small set of vertices. Okay, so think there's a almost D clique here, and maybe there's one edge here or one edge here. Okay. So now globally, this is a pretty sparse cut, but it's easy to verify that at least initially, so you will end up actually decreasing the cut size. Okay. So this kind of monotone, simple monotone arguments don't work. So what we did is take a completely different viewpoint on this, okay? And the main idea is the following. Okay? So the main idea is to look at it from a very linear algebraic perspective. Okay? So let's look at the adjacency matrix of the graph, okay, and see what happens to it as you do this procedure. Okay? So you have this adjacency matrix. Suppose UV is an edge, so you have ones out here and zeros on the diagonal. So what happens in one step? Okay. So what you will do is take a 1 from one of the columns, put it in the other column, and a 1 from this column and put it in the other one. Okay. And which one you pick is chosen randomly. Okay. All right. So it's easy to convince yourself. You think about it a little bit that suppose you fix suppose you always pick the middle edge to be uv, okay? Then you can actually write down the expected uth column of the adjacency matrix in terms of the matrix that you have right now, okay? So, and this is actually pretty easy to see because I mean, you'll actually, with probability 1 over d minus 1, you'll add this as a neighbor to this, to vertex v, right? So you can actually see that this, that the column at time t plus 1, at least in expectation, is a clean average of the column at time t and the column for v at time t. Okay? So in some sense, the adjacency vectors are basically getting averaged in expectation, okay? And we have a discrete version of this process. Okay? And this is the main idea behind our analysis, that in expectation there is some clean averaging of adjacency vectors that's going on, and if everything mixes, then you expect all the adjacency matrix vectors to be like uniform. Okay? So that's the general idea. And it turns out you can go one step further. You can write down, suppose you know the Laplacian of the graph at the current step, you can write down the expected Laplacian at time step t plus 1. Okay? And it turns out there's a clean formula for this. Okay? So you can write it as, so let's not get into the details of this expression, but this turns out to be the expression that you get. And so there are some mild technicalities here because if the neighborhoods of u and v overlap, you have to be a little bit careful how you deal with it so that you don't add double edges and so on. Okay. So I won't go into this, but you can easily come up with a protocol such that this condition holds. Okay. All right. So this is, I claim that this is a nice expression. Okay, so let's see why. Okay, so note that first off, this is some kind of an average between LT and LT square. Okay, and this turns out to help. So let's see what happens to the second eigenvalue. Okay, and so let's do some wishful calculation. So what we know is that the expected Laplacian at time t plus 1 is given by this expression, right? So let's see what happens in expectation to the second eigenvalue. Okay. So here basically the eigenvalues evolve the same way as the matrix does because these are all, they have a common diagonalization. Okay. So the second eigenvalue, it actually improves by this factor. Okay. And what you can see is that as long as lambda 2 is small enough, okay, as long as lambda, I mean, if lambda 2 is already big, then it means that you're already an expander. Okay, so if lambda 2 is smaller than d over 3, then this term will be roughly d. Okay, so it will be order of d, and so you get an increase of roughly 1 plus 1 over nd factor. Okay, because this will be d and it cancels out one of the d's here. So this is pretty nice because what this is saying is, as long as you are not yet an expander, your lambda 2 increases by a 1 plus 1 over nd factor. Okay? So technically you might expect to be done in something like O tilde nd steps. Okay? So this is why we also conjecture that you will be done in so many steps. Okay? But as I said, this is just wishful calculation. This is only the evaluation of the lambda 2 for the expected matrix. Okay, so this is not quite how the matrix evolves. Okay, so we really need to argue about the expected value of the lambda 2, not the lambda 2 of the expectation. Okay, and it turns out these two are not related in this nice way. The opposite turns out to be true. Okay, so all right, but this is actually something that appears in a broader context, right? So what we are saying is you have a matrix that's evolving. You know that the expected evolution is nice, okay? And this sort of a thing, and you want to show that what you have at the end is close to the expectation, okay, at least spectrally. Okay. And this sort of a thing is, appears in many contexts, like in analysis of stochastic gradient descent and so on also, you have this phenomena where the behavior in expectation is good, and you want to show that you keep making progress towards this goal. Okay. And we actually use some ideas from these kind of analyses. Okay. So it turns out that the main reason this argument doesn't work is because arguing about lambda 2 doesn't work, is that lambda 2 is a very non-robust quantity. Okay. So if you change the graph a little bit, you can actually significantly increase, or what's even worse, decrease the lambda 2. Okay? So that turns out to be the main issue, and we get around it by working not with the smallest eigenvalue, but with what is called the soft min. Okay? So the soft min of a bunch of numbers, I'll define it in a second, it's basically a more robust version of the min. Okay? So this is a common trick that people do in optimization. Okay? So what is the soft min? Okay. So suppose you have a bunch of non-negative numbers, so a1 through an. Okay. So you can define the soft min. So this is something that's parameterized by mu. Okay. And it's basically, you take the sum of the exponentials of e to the minus mu ai, and you just take the logarithms and normalize accordingly. Okay. And what you can see is that if there's only one number that's big, and the rest are small, one number that's small and the rest are big, then it actually gives you something really close to the min. Okay? So this is easy to see. But even otherwise, turns out it doesn't do too badly. Okay? So it turns out that the soft min always lies between the actual min and the actual min minus log n over mu. Okay? So mu is the smoothing parameter that kind of determines how close this approximation is. So this comes up often when one is analyzing various convex optimization techniques. Okay. So how is it useful in our context? Okay. So we have we have this Laplacian matrix that's evolving, okay, and we look at the soft min function applied to its set of eigenvalues. Okay. Because we want to reason about lambda 2, we will actually argue about the soft min of the eigenvalues. Okay. And that is essentially like looking at this potential, which is basically trace of the exponential of e to the minus mu l. Okay. And so we can keep track of this potential, and some simple observations. Because lambda 1 is always 0, you know that lambda is, this phi is always bigger than or equal to 1. And one thing to note is that if you have a tiny eigenvalue, if you have even one eigenvalue that's smaller than or equal to 1, then this phi is at least a constant more than 1. Okay, because one of these terms will be pretty big. Okay. And in the opposite direction, if you know that phi is actually smaller than 1 plus 1 over n squared, then you know that the graph is an expander. Okay. So then you know that there's exactly one eigenvalue that's close to 0. And this is what we will show. We will show that if the graph has already not become an expander, then this potential keeps dropping, and eventually it will drop to something like 1 plus 1 over n squared, which means that you get an expander. Okay. So this is the general outline of the proof. Okay. And how much time do I have, by the way? 5 minutes? Okay. I'll try to wrap up in 5 minutes, because most of this afterwards is, so this is the general outline of the proof, and I'll give a brief idea of the technical things, because it's the last talk of the conference. Okay. So we'll think of setting mu to be a constant and degree to be 100 log n, just to be clear for this. So it turns out, so there's one nice thing in the analysis, which is how you analyze this drop in potential. Okay. So you have this potential, and you want to show that if your graph is not yet an expander, the potential drops by a reasonable amount. Okay? And the key trick is this linearizing, okay? Because you know that this Laplacian evolves as Lt plus 1 being Lt plus some xt. And xt, all you know about it is that it's small, because there are only a few edges that change in the graph. Okay? and you also know its expectation. Okay, and you want to show that the expected behavior actually somehow comes through. Okay, so you want to somehow make this phi as some kind of a linear term, and that's exactly what you can do. So it turns out you write this out, and there's a standard inequality called the Golden-Thomson inequality, and then you can simplify. It turns out that the choice of mu can be used to make this quadratic term negligible. Okay? So you can show that the linear expansion for this phi t plus 1 is actually the correct one. And at this point, you can essentially take expectations, because you just have, so you look at the expected value of the potential, and that you can say is essentially the expected value of this, and if you ignore this, it's just a linear term. Okay? So that's the main idea in the analysis, and you can write out some calculations, and it turns out that getting an n-cube bound is actually pretty easy. Okay, so you can show that the drop in potential at every time step, okay, is at least a factor of 1 over n cubed times the potential at time t. Okay, so what this shows is that if you have not already become an expander, then the potential actually drops by a factor of 1 over n cubed in every time step. Okay, and so this means that if you take so many time steps, then the potential will halve, and so if you take this times log n many time steps, you actually come arbitrarily close to 1. Okay, so that's the general outline of the analysis, and you can actually improve this part of the analysis a little bit, and you get a factor n squared bound. Okay, but n cubes actually turns out to be fairly easy to get. Okay. So the conclusion of this is basically we considered this problem of analyzing this so-called the flip chain, how quickly it converges, and we gave a simple and more direct analysis instead of going through the usual Markov chain comparison type arguments. Okay. And these are also techniques that are more inspired by optimization rather than the typical ones that are used in distributed analysis. Okay. So it's a slightly different technique. And we can also analyze the simpler process that I said before, where you actually pick two random edges and you swap the endpoints. For that, you can actually get a tight analysis, okay, by using the same technique. And but the natural question here is, what happens? Can you push this kind of a method to get an ND upper bound? Okay, so it turns out you can't do it with the same potential, so you have to do something more clever than this. And so that's it's kind of an intriguing question, because it's a very simple problem to state, but we don't know how to show an ND upper bound. Okay? And there's a smaller issue, which is that we rely on D being large enough, and this somehow in random graph theory, this is where other things also break down. So it's not clear if this is an important restriction. All right, and there are also other questions that we haven't quite looked at, which is how do you analyze things when nodes act in parallel? Okay, so that's an interesting question, and it's also interesting to study what happens when nodes come in and go out. Okay, so how quickly do things mix when you add a new node and stuff? Okay. All right, thanks so much.
Type of H flip, still local, but perhaps more.
Yeah, so we thought about it. I don't know actually. So it's not clear if you just look at a small number and do it. There, I don't believe we can get much better. Yeah. I mean, this itself we expect it to be ND, right? So in some sense, yeah, it's more of the analysis, and we don't know how to analyze that either. So the same kind of issues crop up. It's mainly this exponential potential, and somehow getting beyond n squared for that is tricky. All right.